So today I'm going to speak about a project we did with Raphaël Porcher, Virgit Tran, and François Petit that will mention treatment effect estimation in randomized trials with AI augmentation control arm. So it's a complicated title, but we'll try to say, let's say, plain. The idea is recruiting people in clinical trials is hard, and many trials go to discontinuation because we don't manage to recruit them. And over the last years, both the European Medicine Agency and the Food Drug Administration authorized the use of externally controlled trials. So basically the idea is that you have data on the control arm from another study, and you do some statistics of them in order to use them in your new study. And some people thought that, all right, now we have generative AI, and therefore we can generate patient data. And from this patient data, maybe we can learn something about what will happen to the control group of our study. And in general, if you're a statistician, that's the point where you start to say, wait, they want to do what? Because what is claimed is that you can start a trial, you recruit normally, so you assign people to the experimental arm and to the control arm, and at some point you stop, and you say, all right, I will continue to only recruit people in the experimental arm, train an AI model on the control arm I have, and generate the rest. And so far, if I do that, what I gain is that I only need to recruit 3/4 of the planned sample size, and therefore I save both ethical concerns and finance concern. All right, but some people that know a bit more generative AI, they can say models, they have stochasticity. So if you generate some patient data, it will change from each time you generate. A bit like when you use ChatGPT and you ask 2 times the same question and it gives you different answers. And what we did here is to remove the stochasticity by doing a large-scale experiment where we train many models and look at what it will answer in many circumstances. Here, at the end of the day, we are in a quite common situation in engineering, and I'm pretty sure in medicine or public health, is that are we using the right tool for the right use? The idea here is my tool can be really efficient. If it's not efficient to the task I'm asking, then I might be overconfident and say something really confidently that is totally wrong. So here are generative AI algorithms that generate patient data based solely on the trial's information, good for trial augmentation. And for many reasons that I will describe later, this is an illustration of why this would be a really difficult task and most probably a task that will fail. So what did we do? We did exactly what was planned, and we obtained 2 treatment effects, the one from the real trial and the one from the trial where you do the augmentation. And if your augmentation is reasonable, you should expect that both treatment effects are the same. Roughly, you want to obtain what you would have obtained with a normal trial, and here we have the actual answer. You remove the stochasticity by saying, all right, now I do that 1,000 times, and I average it out. And you can say, all right, maybe it's complicated because you only have one trial, and this the first part of the control arm here, the X%, they are not representative. So what we did is, instead of stopping the recruitment after a certain point and replace the patient that would come after, is that we randomly remove patients and replace them to simulate the fact of having a different recruitment. One point is that from a statistical point of view, it seems odd to be able to do that, to be able to extrapolate that way. And what I want to stress is that in the case of generative models, it creates new caveats and new questions that we need to ask. For instance, in the first talk, here the formula apparently was really clear without the tilde for someone that is an expert. With the tilde, sorry. But if you add it, then it might be false, and only an expert can see that it's false. So you have new questions that you need to ask yourselves. And in order to be quite broad, we varied in 2 large trials. It's not really a problem of the architecture itself, so we varied the architecture on it. And also we stop in recruitment after 10% for the small trial, 25%, and half of it. And one point that I want to also stress is that you can look at 10% and say, okay, it's low. It's 10% of 20,000 patients, roughly. So 10% of the control arm of the international strike is really big for a clinical trial. And how do we measure it? So how do we measure this augmentation technique to the task that we are looking for, namely augmenting randomized trials? Here, we inspired from metrics that are used in target trial elimination, and we look at differences in absolute risk difference. So you have a treatment effect, and you look at the difference in between them. Significance disagreement, which means that are country trials that are augmented able to give you the same answer in terms of positive or negative trial than the actual trial with the normal procedure to do it, the randomized control trial. And a third metric that is more statistically sounding, which is incompatibility of result. Here it's just to say that both confidence interval from the augmented procedure and the normal procedure do not overlap. This, you want it to be 0. They should overlap, really, like in almost all cases. And here are the results. So there are many things on that figure. First, you can observe a clear correlation. You have basically a line that you can fit, the x equals y line in between the two, which tells you that you obtain the treatment effect that you have in the training set. So, and this is not surprising when you look at how those models are trained. And therefore, first, you already have the answer of which treatment effect you will obtain after augmenting with a generative AI algorithm. And second, is if you believe that this treatment effect is representative of what a real trial would do, why would you augment then? Then you have multiple colors. You have red boxes and blue boxes. All the red boxes are not agreeing with the trial. The international stroke trial is negative, and here you find significant effects, both negative and positive. So you can say that you have an effect, and you can also say that you have an effect that is significant in the other way. And in terms of the incompatibility result, so these questions of overlapping confidence intervals, it's the blue histogram on the right, which tells you with the dark blue that you actually have some cases where those confidence intervals do not even overlap. So here are the more detailed results, and you see that, for instance, in the risk difference, if you only do the normal procedure, namely the one that I described, where you recruit people, you stop, and then you replace by generated patients, then you can have an effect that is up to twice the effect size of the actual trial. And if you do the random removal procedure, so the second one where you remove some patients and replace them by generated data randomly, uniformly, then you obtain a significance disagreement up to 65%, which means that 65% of trials would lead to a different conclusion in both directions, positive or negative, both significant. And you have an incompatibility of results that go up to 25%. So yeah, confidence interval do not overlap in 1/4 of the generated trials that we did. Here, why is this, from, let's say, a statistical point of view, sounding? First, you have the idea that those, if you look at those models, they're trying to replicate some statistical property of what they observed. One property is the mean, and here we look at the mean in the larger population. So if you reproduce the mean, you reproduce the difference of the means, and in here you predict the effect. You have also you can say, all right, but if I have continuity, it's a bit what I explained earlier. If I have continuity along recruitment, then this would work because I would observe the good effect at the first place, and then the effect would be good because it's reproduced. Fine, but how do you prove that first what you observed will be continuous in the sense of it will be monotonous, like you will not change the effect over recruitment? And when you do that, you add variance. So how do you ensure that what your augmenting procedure is doing is not just adding noise? And a more generic thinking is, all right, if it's the data processing inequality, which means if you do some statistical, let's say, transformations post-processing, then you cannot increase the amount of information you have in your data. And therefore, basically, the only way you can say something more precise is by extracting more information, but the way we extract information already in a trial is quite efficient. So there are not that much you can gain from new techniques. Is it over? Are those models useless? No, for different reasons. First, I mentioned information. And here, the problem is that this procedure is really endogamous. So you use the same information in order to produce new patients, so you bring nothing more to the trial that you did. But suppose that you manage to bring something more by foundational models that have seen basically everything and can understand some part of either the disease or the treatment that is not present in the trial. Then you might earn something. If you manage to incorporate either informative priors or some mechanistic approach, you have an understanding of the binding of the protein or something, and you manage to put it in the loss of the model, maybe you can obtain information on certain patients. And in general, if you stay totally endogamous, synthétiques data, they have proven to stabilize the effect on some other algorithm. For instance, if you try to learn individualized treatment effects, then you know that if you train on larger data set, it will not give you this extrapolation ability that I mentioned earlier, but you will stabilize your training. And in privacy, you're basically, when you want to share a private data set that contains patient data, what you want to do is not to give the patient Y information to the other clinician. What you want to do is you want to give a really precise description of the statistical property of your population that you observed to someone else without giving any personal information. And here, these models, they can, with the proper training, do this. Namely, have all the statistical information that you want, while never giving the actual information about one single person. And roughly, that's it.
Do you have a question?
Thank you very much. Very interesting. When you are generating the treatment effect for the half of the control group, how do you deal with the baseline characteristics? Because now the randomization is not. You are removing the randomization. How the baseline characteristics are helping to predict the outcome that you are generating in with AI? By baseline characteristics, I mean the SES, the age, these things that we assume by randomization, we assume that the distributions of these variables is the same. Now that after randomization, you are generating for the second half of your control group, how you take into account these variables?
All right, I think I see what you mean. The thing is that by randomization, you expect that at the middle of the trial, you already have basically a good representativeness of the baseline characteristic. What is hard to learn here is rather the correlation in between the outcome and the baseline characteristic, and that's what power gives you in fact. So if you need to have a representative set of the age distribution in general after 1,000, 5,000 patients, it's fine.
Thank you, very interesting. If I understood well, the issue arises because the distribution of effect modifier for patient that you generated is different than the distribution that you would have obtained if you recruited the whole arm, right?
Not necessarily. You can have that can happen, but you also have that in the extent to which it's an effect modifier. So what let's say the modification that it will do to the outcome, you learn it with a certain, let's say, noise around it. So you're not certain about it. And this is also increasing. So you might just by luck have, for instance, something that appears as not at all an effect modifier, but by iterating over more and more patients, you will see that it's an effect modifier, and like at some point you will recognize it. So the idea is more that you don't have the power to observe exactly what you want with the certainty that you want.
So I was wondering, for for example, the extreme cases in your figure, like,
Yep.
have you looked at what happened in those very, like, very specific cases, like on the upper right and lower left?
Oh yeah,
Like the cases where the overlap is, like, there is a very huge gap between the confidence interval
Yep.
that you generated and the one you observed.
The thing is that due to lock, you can pick a set of, in the training set, due to lock, you can just pick 1,000 patients that responded well or badly to here it was an active control. So like you can pick people that died after 6 months, and all of them suppose died after 6 months, and this can happen due to lock. Suppose that you pick 2 patients. Then like it could totally happen that you pick 2 patients that both died, and then your representativeness of your control group is everyone is dying. And that's what happens in those extreme cases.
Thank you.